So when we talk about equilibrium, we're talking about a state that involves sameness and constancy. So what do you think of when you think of equilibrium? Equality? Balance? It's like you're like, I need to recover my equilibrium, right? You need to get balanced, figure out which side is up, just get sort of settled, right? And that's related to what a chemical equilibrium is. It's balanced. In terms of sameness and constancy, what we're going to see is that the concentrations or the amounts of reactants and products are going to be the same. And so from the surface, it looks like nothing is changing. And yet, if we were able to zoom in and look at the individual molecules, we would see that there's actually a lot of stuff going on. But when we talk about a chemical system being at equilibrium, we're talking about the rate of the forward reaction being equal to the rate of the reverse reaction. So on that freeway, the number of cars going north in a given amount of time being equal to the number of cars going south in the same amount of time. The number of cars at the north end and south end of that stretch of freeway would be the same, but are they the same cars? No, they're not, because there's this back and forth thing going on. When we talk about a rate of a chemical reaction, it's a measure of how fast the reaction proceeds. Just like a rate of speed is how fast you're traveling. So we define it as the amount of reactant that changes to product in a given period of time. We can control reaction rates if we understand the factors that influence them. And that's why we study equilibrium, because like in an industrial process, you may want this reaction to go faster. If we understand how it happens and what affects the rate, then we can affect or change the conditions and cause it to go faster. Yeah. So we have to understand how do things react, and this involves collision theory. Theory is explaining why something happens, not just stating this is what happens. So this is our explanation for why and how. Most chemical reactions have an activation energy. This is a barrier, an energy barrier that has to be overcome for the reaction to proceed. Many times this is the energy required to begin breaking the bonds of the reactants. For the reactants to form into the products, there may be bonds that have to be broken. That requires energy. The factors that influence the rate of reaction are going to be the same factors that influence the number of collisions that occur per unit of time. In order for two reactants to react, they have to run into each other. So in this example with hydrogen and iodine, one hydrogen molecule and one iodine molecule can react to form two hydrogen iodide molecules. But if these two molecules never come into contact with each other, will they react? No, they won't. So in order for them to react, they have to come into contact with each other. They have to collide with each other. So the rate of a reaction generally increases when we have an increasing concentration of reactants. And that's just an observation. If we increase the concentrations of the reactants, the reaction occurs more quickly. Well, why is that? Well, if you have a higher concentration, you're going to have more collisions. So here in panel A, there's 4 molecules of each reactant, and down in panel C, there's 8. So the concentration is doubled. These are gas molecules. See the state here, it's gases. So these are gases, and what do we know from kinetic molecular theory of gases? What are these doing? They're just moving. They're moving in a straight line until they run into something. then they bounce off. It's like a Pong game, and they just keep going. You have a potential for a reaction when an iodine molecule and a hydrogen molecule collide. Nothing's going to happen unless they run into each other. So when the concentration is higher, when you've got more molecules in the same amount of space, they're going to run into each other more often, right? The analogy in chemistry land has to do with romantic relationships. Can you fall in love with someone if you don't know that they exist? Not really, no. Not real love. You need to meet them, right? Run into them. So where's a better place to meet people? An alfalfa field or a bar? Neither. Well, neither. That's excellent. Where are you going to meet more people, though? In the bar. Why? Because there's people in the bar, right? You can't meet people in an empty field. There's no one there to meet, right? So in order to meet someone, you have to go where people are, right? It will increase the chances of you finding someone that you're compatible with. So higher concentration of reactants means more collisions, more potential reaction. As the reaction proceeds, what happens to the concentration of the reactants? Does it stay the same? It decreases because this iodine and this hydrogen react, and now they're not hydrogen and iodine anymore. It's a little bit like you've got this big room of people, and maybe you're doing one of those speed dating things or something, and when a guy and a girl decide that, hey, I want to get to know this person better, then they leave the room. They're not in circulation anymore. And so after a while, the number of people that are available to meet goes down. The concentration goes down, right? Then the rate of the reaction, the rate of you meeting new people goes down. So the reaction rate will go down as the reactant concentrations fall. As the reactants react, they're no longer reactants, and the rate of the reaction goes down. The rate of a reaction will generally increase with increasing temperature, because raising the temperature makes the molecules move faster. When they move faster, you have more collisions. So here, these are equal concentrations, but these little blurs are telling us that this is a higher temperature. These guys are moving faster. If they are running around the room, they're going to bump into people more frequently, right? And those collisions are going to occur with a higher energy. It's not enough for the two molecules to just very, very gently bump into each other. That's not going to provide enough energy to break the bonds. They'll just kind of bounce off of each other. If they collide with enough force, a reaction can occur. So by raising the temperature, we have two things that cause the reaction rate to increase. We have more collisions, and the collisions have higher energy. So reaction rates increase with increasing reactant concentration. Reaction rates increase with increasing temperature. And the reaction rate will decrease as the reaction proceeds. You have a given amount of each reactant in a container, and as the reaction proceeds, the concentrations of the reactants decrease, and so the rate decreases. So let's see if we're understanding this. In a chemical reaction between two gases, you would expect that increasing the pressure of the gases would probably do what? Increase the reaction rate. Good. Why is that? I couldn't hear you. Let's say the volume is the same, so the volume doesn't have anything to do with it. But if you increase the pressure in the same volume, what has to have changed? The speed, the temperature has to change, or the number of moles of gas has to change, right? And so the pressure, now we've concentrated essentially the gas, so it's either moving faster and or there's more of it, and so we're going to have more collisions. More collisions will increase the reaction rate.